Let's talk about symmetric encryption and the issues involved in symmetric encryption. Symmetric encryption algorithms, most common type of cryptographic algorithm. The book says it's also called private key cryptography. I don't really like this terminology, and I've really not seen it in any other book, so I would take that with a grain of salt. Symmetric encryption uses a single key, and this is important, you have to understand this, uses a single key to encrypt and decrypt a message. So the same key is used both for encryption and decryption. In some situations, we refer to this as a session key. And we'll talk about that later. I have another movie I'll do on that in something called SSL, Secure Sockets Layer, which is now morphed into Transport Layer Security, TLS. We refer to this key as a session key. So that'll be another thing we can go over to get a grip on this whole encryption thing. It's essential that the key, since there is only one, we call it the key, be kept confidential. If an attacker obtains the key, he or she could decrypt any messages sent with that key. So key management is an issue with symmetric encryption. You can classify these algorithms into two distinct categories based on the amount of data processed at one time. There's stream ciphers. The simplest example of this is a substitution cipher, a simple substitution, or block ciphers. Substitution ciphers generally aren't that they're not that good an idea. They can be easy to break. So in general, your block ciphers are going to be the way you want to go here. A block cipher manipulates an entire block of plain text at one time, and for larger sizes of plain text, the algorithm will just handle multiple blocks until it makes its way through the entire plain text. The plain text message is divided into separate blocks of 8 to 16 bytes, and each block is encrypted independently. Furthermore, the blocks can be randomized. Again, there's some pretty serious mathematics behind these things, and I'm going to spare you the gory details. You just need to know the major types, the major brands or names, I guess would be a better way of putting it, key links and things like that. So we've looked at almost the same picture, same graphic before, and again the flow goes this direction from sender to recipient. As before, we have a sender, we have some plain text that we feed into the cipher or the algorithm, along with a key. Again, the key is a number, and it's going to be longer than 594. So we get our ciphertext out, we transmit the ciphertext across the public network. At the recipient end, we pass the ciphertext into the cipher along with the key. In this case, notice it's the same key. As I pointed out a couple slides ago, we only have one key to work with in symmetric encryption. So we feed in the same key into the cipher, and we recover the plain text that was, and that's equivalent to what we've sent by the sender. So there's a couple things you can remember about these symmetric encryption algorithms. They tend to be fast. And the reason they're fast is relatively small key sizes. Now you'll see here in a few moments that we're talking sometimes 128 bits, sometimes 256, sometimes more than that. But that's really there are much longer keys that we use for other purposes. So in general, smaller keys gives much faster response than larger keys would give. So let's look at some of the particular types of encryption algorithms. There's one called DES, Data Encryption Standard. This is one of the most popular ones. It's still being used. Unfortunately, it's no longer considered to be secure. It's only based on 56 bits. This can be cracked with by using fast computers. So DES is not a good idea. It has been improved with something called triple DES. Now, if you're wondering what happened to double DES is only slightly better than the original DES due to some idiosyncrasy in the algorithm, so it's not going to be used. Triple DES does 3 rounds of encryption instead of just 1. The most secure versions use different keys for each round, so triple DES is not a bad solution. The government, led by the National Institute of Standards and Technology, which these people have an interesting website. They're very, very serious about what they do. Led by the NIST, in late 2000, basically they had a competition for a replacement for DES. And they chose this advanced encryption standard algorithm. It's actually an algorithm called Rheindahl, and it was developed by some academic types from somewhere in Europe. I can't remember exactly what university they were from. But this has become the official standard of the U.S. government. And it can use different key sizes, 128, 192, 256 bit, for example. 192 and 256 are required for things that are referred to as top secret by the government. Again, longer keys are harder to crack, and they're slower, but they're harder to crack. So another symmetric algorithm, there's actually a family of these. They're called RC with a number. These were designed by Ron, I think his name is Revest. He's done a lot of work in cryptography. The important thing is here, if you're going to go take the Security Plus exam, is the number of bits. If memory serves me well, RC5 is the one we use the most, and it's 128 bits. I thought we had another slide, but I was wrong. There's IDEA, used extensively in Europe. Again, 128 bits. So again, to review here, longer key lengths are going to be better. They're slower, but you got more security. And the thing you want to remember here is for these keys, we don't want to encrypt a lot of plain text with any one of these keys, because the more things you encrypt, the more things that are out there, the more things that these cryptanalysts can look at and maybe discern a pattern in the output, and therefore work backward and figure out what your key is. In essence, crack your code. So what we typically do is we use these keys briefly, and then we generate a new key and use it for a little while, and then we generate another key and use it for a little while. Now, the big problem with symmetric encryption is how to move the keys from the sender to the recipient, and there's a way to do this using a different type of cryptography called asymmetric encryption, and we'll look at that in the next movie. So you can be thinking about those issues. Finally, blowfish. It's another block cipher. It can have key lengths anywhere from 2 or 32 to 448. Blowfish was in the competition for the AES. It didn't win. A lot of people do like blowfish, so it is still being, or it is being used. Notice you can go up to 448 bits, which is quite long for a symmetric key algorithm. So again, symmetric key encryption uses the same key for both encryption and decryption. Most of these keys, 128 bits, maybe 256, maybe conceivably could be larger than that, but it's actually kind of unusual to find anything in much use more than 256 bits. And these are relatively short length keys, so these algorithms, these symmetric key algorithms, are pretty fast, relatively speaking. We'll look at a different type of encryption called asymmetric encryption that uses much longer keys and therefore is much slower, but it's more of a special purpose type of encryption. So that's the strengths of symmetric key encryption. The big drawback of symmetric key encryption is how do you get the key from the sender to the recipient without it being intercepted and therefore being made worthless. And the answer to this is actually asymmetric encryption. We'll look at this in other movies.